Hi all. In this video, we're going to look at how to use integration to find the area bounded by given curves. So let's start with where this concept is coming from before we use it to solve some problems. So firstly, we know to say that if we have a rectangle of some sort, let's say something like this, or it can be something like this, then for such a case, let's say this is the length and this is maybe the width or the breadth, like that. And here we can say this is the length and here we have the thickness there. So the area of such a shape is equal to the product of the length times the breadth in that way. So this is how we get the area of a shape. Now imagine if instead of giving the exact values from edge to the other edge, instead you're given values to say this is at point what and so on. What do I mean? Let's say you have an x-axis and the y-axis. Let's go white for that. So you have, let's say, a vertical axis like this and the horizontal axis like this. And instead of being given the exact length and the width, our shape is, let's say, somewhere here. But you're told to say that this is, let's say, at 2. This is, let's say, at, we can say 5. And you can say this is, let's say, at 6. And this is, let's say, at 1. In this case, clearly, you can tell that the length will be the difference from the top point minus the bottom point, and the breadth will be the rightmost value minus the leftmost value. So this gives us a 3 here, and here we end up getting a 5. So when it comes to getting the area of this shape, now we will just multiply, we know we're using L times B, which is going to be 5 by 3, and of course this gives us 15. Since I didn't specify the units, whether these values were in centimeters or meters, so here we just say square units. Okay, so this is the logic we're going to be using. Now imagine, you see, this is, here I'm picking a rectangle. So what if it wasn't a rectangle? What if it was a random shape? How would we approach it? So now for random shapes, areas enclosed by curves, to get their area, we utilize the concept of integration and how it can be used to sum up multiple expressions. Let's say you have an area bounded by a curve like this up to maybe some value of x somewhere here. Let's say here x is equals to b, and it starts from the origin where x is equals to 0. So let's say that's point A. So let's say I wanted to find the area bounded by this this graph. So we can say that the graph on top, let's say it's controlled by an expression f of x. So the area we're going for is the area between the function f of x and the x-axis, or the graph y is equals to 0. So we're going for this area here. So let's just shade it up so that we can see it properly. So we see that this is clearly not a rectangle, and of course it's not a triangle. So how can we find its area? So to do that, we're going to use integration. And the logic here is that we want to view this shape as if it was made up of many tiny rectangles. So we'll divide the whole shape into tiny rectangles. Let's say that is one such rectangle. So running all the way from the lower boundary, which is the x-axis, up to the upper boundary, which is the graph y is equals to x squared. So these rectangles, of course, are assumed to be very, very thin and to be a lot, spanning from this side where the height is almost 0, and then becoming more and more longer as you go up. So such rectangles. So if this was made of tiny rectangles, spanning all the way from x is equals to a to x is equals to b, And we can find the area of each one of those rectangles, because we know for the rectangle, all we have to multiply is the thickness of each one of these multiplied by its own height. That will give us the area of that small section. So because we're picking a small section, its area, we're going to take it as a differential area, dA. So if my section, the one selected, is a vertical section, then the length is going to be this side, and the thickness here, notice that it's in the horizontal axis. So the thickness, I'll take it as a change in x. Basically, we're just saying this is a change in x from the smallest value of x to the maximum value of x for that selected section. So in the end, the differential area will have an area obtained by multiplying its length by its thickness, dx. But what's the expression for this length here? So notice that the lower value, or the lower end of our rectangle, is controlled, let's say, by a function g of x. In this case, our lower function there is controlled by y is equals to 0. And the upper part in our case is controlled by a graph, or the function f of x. So to get the length L, which is the height, basically, we'll subtract its higher end, its higher boundary, minus its lower boundary, g of x. So we'll do it like that. So with this done, when we bring them here, where we have L, we now have the upper boundary minus the lower boundary, and then dx. So this becomes what we use to obtain the area of the selected differential section. So this is just the area for, let's say, one such rectangle. But now to sum, because we know an integral can be used to get a sum over multiple values or expressions. So to now get the summation of all such rectangles spanning from the smallest value of a to the largest value of a, we're going to use an integral. When you integrate on the left side, we'll remain with the overall area now. On the right side, we'll have a to b, and then we are integrating f of x minus g of x with respect to x. Now, if here you have dx, then the limits of integration, this will be the smallest value of x, this will be the largest value of x. In our case, the smallest value of x is a, we're generalizing, the largest value is b. And the lower boundary, the g of x, is the line y is equals to 0. So basically, we'll put a 0 there, and this becomes from a to b, and then we have whatever f of x is, minus 0 there, dx. So this is how it would go. Let's pick an example from here and see how we work it out. Let's go with the first one, where we have y is equals to x squared minus 2, and the line y is equals to 2. So I'm going for the area bounded by the two curves. As you can see, the first step is always to try to sketch or picture the problem. So here we have the two graphs. So how do we sketch these? So all I know is that y is equals to x squared minus 2. That has to be quadratic. That is quadratic. So, and seeing that x squared is positive, I know my quadratic is curving upwards. And other than that, what else is there? I know it has to go downwards, or when y is 0. When x is 0, which is along the y-axis, y will be negative 2. So I'm looking at something like this. So that when x is 0, y will be negative 2. So this graph has its turning point. Let me try to see if I can get it to be symmetrical. So you have something like this. Okay, better. Okay, so we have something like this. When x is 0, y will be negative 2. I can also get the intercepts here and there, but for now, we'll leave them out. Next up, we have the second graph, y is equals to 2. Y is equals to 2 is a horizontal line. Let's say this is our line, y is equals to 2. So here we have y is equals to 2. The other one, we had y is equals to x squared minus 2. So this is what we have. We're going for the area between these two graphs, or bounded by the two graphs. Okay, let's just shade it so that we know what we are working with. Okay, so this is the space we're trying to sort out. So just like before, you want to understand what section are you going to pick. Here you can pick vertical rectangles. You can also pick horizontal rectangles and so on. Basically just the two, you can work with the two shapes. So if I'm going for vertical sections, then they'll be this way. Horizontal sections will be that way. If I'm picking vertical sections, they'll be this way, like that. So they're starting from here and they're going all the way up to the far end this side. And in this case, notice that if my upper part, which is my straight line, is taken as my f of x, and my lower boundary, which is this graph, is taken as my g of x. So I have f of x on top and g of x down. So that when I want to get the area, I'll have the integral from a to b, f of x, the upper boundary minus the lower boundary, dx. So what is our upper boundary? Y is equals to 2. So we'll put 2 there. Since in this case, since we're going for dx, you want these functions to be in terms of x. So there should be y is equals to some expression that has only x and constants. So if this was a dy, then you'd want this to be x is equals to a function of y this side. Okay, so for the first one, our f of x, we have y is equals to 2. For the second one, g of x, again, that one we're given the quadratic there, y is equals to x squared minus 2. So I have y is equals to x squared minus 2 dx. So what will be the values for a and b? So I can simplify this or bring the values for a and b in a bit. We have 2 minus x squared, then this becomes plus 2 dx. So what is our a, what is our b? Since our integration is with respect to x, a and b are values of x. A is the smallest value of x, which is the value of x at this point. B is the largest value of x, which is the value of x at that point. Since what we see here is that at a and b, the two graphs do intersect, so we just have to equate them. One is y is equals to 2, the other one is y is equals to x squared minus 2. Since they have to be equal, then their right-hand sides have to be the same. So you have 2 has to be equals to x squared minus 2, or x squared minus 4 has to be equals to 0, implying that you have x squared has to be equals to 4, or x has to be equals to plus or minus 2. So we're seeing that the smallest value has to be x is minus 2. The largest value is x is equals to positive 2. With the two values now known, we can get our area. The integral from minus 2 to 2 of, so that is going to be 4 minus x squared dx. When we integrate here, we'll have 4x minus x to the power 3 over 3. So this is from minus 2 to 2. So let's bring in our limits of integration. When you substitute the lower limit, the upper limit first, we'll have 4 multiplying 2 minus 2 to the power 3 over 3 minus, now the lower limit, 4 multiplying minus 2, and then we'll have minus 2 to the power 3 over 3. So the first part will be 8 minus 8 over 3 minus, this becomes, I can keep it like this first, minus 8 here, and then this will be plus, when the minus comes from there, 2 to the power 3, that will be 8 over 3. Remove the brackets, we now have 8 minus 8 over 3. This becomes plus 8 minus 8 over 3. So that we have 16 when the 8 and the 8 adds up. And again, this will also give us 16 over 3. So now we just have to simplify this. So here we get 48 minus 16 over 3, which reduces to 32 over 3. Since this was area and we were not given the units, so we'll just go with square units. So this is how we go about it. Let's pick another example that we can work out using this approach very fast. So this time around, I'll go for E. And in E, we have X. So you have X is equals to, we can go with this. X is equals to Y squared. In the line, X is equals to Y plus 2. So just like before, first step is to create a graph so that you can picture exactly what you're looking at. So when you plot, you should have something like this. So that is after plotting your graphs. So after plotting these, let's try to see if we can evaluate the area between them. Now for this one, I really don't want to try the vertical sections. They can work as well, but the only thing I'm trying to avoid here is one simple complication. Here, from this point going to the left, notice that a vertical section drawn like this, its lower end will be the curve and its upper end will still be the curve. So I really don't want that. Even here, when you reach this part, now the lower end is the straight line, while the upper end is the curve. So you see that the boundaries have changed when we cross through this point. So you can work this out by splitting this into two integrals that you have to evaluate, from 0 to whatever the value of x at this point is, and from that point until where they meet again. So that is one way you can approach it using that. But we see that that is going to be longer. You'd have to solve two integrals. So to avoid that, we're going to pick horizontal sections. So if you now choose a differential section which is more horizontal, you notice that for such a differential section, the boundaries would still be the same regardless of which part of the function you're evaluating. So be evaluating from there all the way until when we reach the bottom. And in each case, the leftmost boundary is the curve, which is the white graph there, while the rightmost boundary is the straight line or the blue graph there. So we're going to use the horizontal sections in this case. So for the horizontal section, how is it going to work? It's similar to the vertical section really, and the only difference is how the thickness is oriented. So if I'm going with horizontal sections, notice that my thickness now is in terms of the vertical axis. So it's a thickness in terms of y. And then the length, the leftmost function, I'll take it as my g of, so this time since this is my dy, so I want these to be functions of y. So I'll say this is a g, a function of y, and the rightmost boundary is a function f, a function of y as well. So now you want to make x the subject of the formula just as these were given, and these are going to be functions of y. So our L is going to be equal to the rightmost boundary minus the leftmost boundary. So let's get the area. So area now will be the integral, the overall area. We know the differential area, dA, will be L times dy. So the overall area is going to be from A to B, and then the rightmost boundary, f of y, minus the leftmost boundary, g of y, dy. Let's substitute. So leftmost, rightmost first, which is the straight line, x is equals to y plus 2. Next, the rightmost boundary. no, left, the smaller one. So leftmost boundary now is, that's the curve now. X is equals to y squared. So here we have just y squared dy. So you always want to make sure that after you make this substitution, all these, there's no x that is present here. If there's an x, you have to go back to the function where the x came from and rewrite it in terms of y. So here the values of a and b, since we're integrating with respect to y, this is the smallest value of y, this is the largest value of y. So what are these values of y? We say that the smallest value is basically here at the bottom, and the largest value occurs there. And here we say that these are just points where the two graphs meet. So I need to know when is y plus 2 equal to y squared, since that is when they meet. So I can say y squared minus y minus 2 is equals to 0. Using product and sum here, I'm dealing with minus 2y, and the two factors here will be 2 minus and 1. Yes, when you multiply this, you get minus 2y squared. When you add these, you just get minus y. So from here, of course, after all is said and done, this is going to be y minus 2 and y plus 1 is equals to 0, or y is equals to 2 and y is equals to minus 1. This makes sense. The lower one is going to be minus 1. The bigger one is going to be positive 2. So the smaller one is minus 1, and then we have a 2 there. So we're integrating y plus 2 minus y squared with respect to y. So when we integrate, what do we get? We get y squared over 2 plus 2y minus y to the power 3 over 3. This is from minus 1 to 2. So now we substitute our limits, upper limit first. So this is going to be 2 to the power 2, that is 4 over 2. 2 there, that is 4. 2 there, to the power 3, that is 8 over 3. Now we go with minus 1, the lower limit. Minus 1 squared will be 1. And then minus 1 there becomes minus 2. Then this will, the minus there will still be minus, so this is 1 over 3. So remove the brackets here. So we have 4 over 2, that will just be 2. 2 with that 4, that is now 6. 8 over 3 minus half. Minus, so I'm removing the brackets, so this will be minus half, this will be plus 2. This will be minus 1 over 3. So now I'm just simplifying this. The 6 and the 2 will give me an 8 there. And then the 8 over 3 and 1 over 3 will just add the numerators, taking it to a 9 over 3. And then we still have that minus this. So this is now 8 minus 3 minus 1 over 3. Is it 1 over 3? I think, no, that's 1 over 2. The 1 over 3 simplified. So I hope if you spot one of these mistakes, of course, just do it correctly. This is just simplification. So next up, we have this will give us 5 minus 1 over 2, which is going to be 10 minus 1 over 2. And finally, 9 over 2. This was area, so you have square units. Okay, so I hope you guys were able to follow through. In the next video, we're going to look at applications in terms of volume. We'll study the disk method. After that, then we'll move to the washer method and so on. But we do have multiple questions for you to try out here. So try them out. Let me know what you're going to find. And if you want to compare notes, you can always reach me through my number. Of course, use WhatsApp. And then I'll be able to respond to you and comment on your solution. And if you do have questions that you might want me to look at, please feel free to share them, and I'll consider them. And if you want to join the online groups, you can still do the same. Now guys, see you in the next class.